Hello guys, so today we're going to have a further look into the skeletal formula. So we were discussing about skeletal formula in the previous class, but today we're going to do some questions on it. So let's have a quick review. So first, so I said that every kink or every end shows represents a carbon atom unless it's replaced by something else. For instance, this represents every corner, every end represents a carbon atom. So 1, 2, 3, 4. It has 4 carbon. So unless it was replaced by something else, so for instance, let's say I put a Cl here, so it's like this. So it's unless something is completely replaced, so now it has 1, 2, 3. Now only it's 3 carbons because something is completely replaced. Or it could be in the end, so 1, 2, and at the end, so it has 1, 2, 3 carbons, but at the end. Uh, if you write OH, so rather now this line is an extension, and this doesn't represent any carbon or any it doesn't represent any carbon. So every kink or every end line shows carbon atoms unless there is any other atom present, for instance like this. uh, and one more thing to note, something's very confusing in the skeleton formula, that is that any the extension or an extra atom is usually shown by an extension. So uh, for instance a Cl, let's see, so we have 1, 2, 3, 4, 5 kinks. So now carbon Cl is attached to this carbon, so it is attached to 1 to the third carbon. So 1, 2, 3. So it's attached to this carbon. So we, by extending a line from the third uh, kink, you have to show the other atom. And similarly, for let's say for showing double bonds, you have to put two lines and show a double bond. And also for like any a functional group, you must also like extend a line from the corner and then write the functional group. So this doesn't represent the end. This end doesn't represent any carbon. Rather, this is an extension line. This is an extended line which represents OH. And we have only 1, 2, 3, 4, 5 kinks. We consider only 5 kinks and 5 carbon. And that's how it goes. So moving on to a hard question. We were doing this in the previous video. So we won't be talking about this in this class. So moving on, we have this question. So the question is, find the empirical formula of phenazine. So our first step would be count the number of carbon atoms. So we know all nodes and all kinks represents carbon atom. So if you count the nodes, kinks, unless it is unless something is completely uh, substituted by another atom, we count every kinks. We consider every corner. So 1, 2, 3, 4, 5, 6, and it's completely replaced by nitrogen. So these are extended line. These are nothing rather than extended line. These are not corners or nodes. So we counted 1, 2, 3, 4, 5, 6. Now we have 7, 8, 9, 10, 11, 12. So we have 12 corners or kinks, uh, which means that it has 12 carbons. So this is the step 1. So we're going to count the kinks and mention and find out the number of carbon. Moving on to step 2, which is that we know that every carbon, every carbon is surrounded by maximum number of hydrogen. So what you're gonna do is like before we're gonna focus on a node and look at how many lines are connected or how many lines are actually going away representing bonds. So we know a carbon must have four bonds. So a carbon is usually so a carbon is connected to another carbon and it's a chain. So we know the last one is so the last one must have the maximum number of hydrogens. So it must have three hydrogens, and the second one two. So likewise, we are going to see the carbon bonded to how many atoms. So we're going to focus at each corner, at each node. We're going to focus at the corners of the node, meaning we are going to focus on the carbon and see how many lines are there, meaning how many bonds are there. So let's focus at this one. So let's focus on, let's say this one, the first, this one. So we see this is a carbon and it is bonded to two other carbon. So it can have more two bonds. So it can actually have one hydrogen and another hydrogen. So it can have two hydrogens. Similarly, these have two bonds, so this can have two hydrogen. This also has two bonds, so it can form two more bonds with hydrogen. So two hydrogen. Similarly, this also has two bonds going away or two lines going away, meaning it can have two more bonds with hydrogen. Moving to this carbon or this corner or this kink, whatever you say, it has three bonds going away, meaning it is connected to three other carbon atoms or three other groups or three other atoms, meaning it has one bond left to bond with, that is, so it can bond with one hydrogen. So one hydrogen. This one also has three bonds, so it can have one hydrogen. These are nitrogen, so we don't count. And moving on to the other corners, this can have this one, two, three. So it has three other bonds, so it can have one bond with hydrogen to make four bonds. Similarly, this can have as this has three other bonds, so it can have one bond only to make four complete bonds. So one hydrogen. This has two other bonds, so it can have two hydrogen. This can have two hydrogen. This can have two hydrogen. So now if you count all the hydrogens that can be bounded, so that is bonded to it. So it has two, so 2, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So what we see is that 20 such hydrogens can make bond. So yeah, so what I was focusing on is that, so let's say this is a carbon atom and it has three lines going away or three lines connected to it, meaning it has three single covalent bonds and it can form one more bond. So if it's already bonded to three atom, yeah. So one hydrogen can bond. So you will just look at how like each corner, you will focus on each corner and see what other atoms it is bonded to. So it has three already bonded to three atoms, so it can have one more bond, so it can have one more hydrogen. Similarly, if we like have something like this, so it has a double bond, so two bond is already used, and it has another bond. So three lines are going away, or it's meaning the meaning is like three bonds are there are three bonds with other things. So only one hydrogen can bond. So only one of the hydrogen can actually sit into this place. So this carbon can have one hydrogen bonded to it. So this was the second step. First one is the number of carbon, second term was number of hydrogen, and the third step, step 3, is to see whether there is any other sort of atoms rather than carbon and hydrogen. So we see that in here we have only two other such atoms rather than carbon and hydrogen. So we have two of them. So we saw that We have 12 carbons, 20 hydrogens, and 2 nitrogen, and we were asked to find the empirical formula. So if we simplify all into the simplest ratio, if we divide by all of them by 2, so we get 6, 10, and 1. So we know when we get 1, we cannot further divide into anything else. So this should be the empirical formula. So that is how you work with skeletal formulas for finding the empirical formula or finding the molecular formula. So moving on to this component, this question which says what is the molecular formula. So the first step, step 1, is count the number of kink or count the number of nodes to find the number of carbons. So let's have a look from the first kink. So we have 1 carbon, 2, 3, 4, 5, 6, 7. This line is an extension. This line, OH, this thing is an extension. So we counted how much? We counted 1, 2, 3, 4, 5, 6, 7. We counted until 7. We have 8, we have 9, we have 10. So we have 10 carbons. We have 10 kinks. Now our step is to count the number of hydrogens. So I've done this hydrogen thing for you already here so that it is easier. So if I zoom into this, uh, so this corner or this, let's say it could be like this also. So we see that this has one line going away, so it has one bond. So this carbon is bonded to another carbon. So similarly, this carbon is bonded to this carbon, and we see it has only one bond. So there are 3 hydrogen that can make possible bonds. So 3 hydrogen. Moving on, this has 1, 2, 3. So let me just erase it and do it again. So this carbon has 1, 2, and 2 double bonds. So it has 4 bonds already. So it cannot have further bonds. So it has 0 hydrogen. So it has 0 hydrogen. This is not an OH, by the way. This is this means a 0 hydrogen in blue. So this is a 0. I mean there is no hydrogens at all. Moving on, this carbon has 1, 2, 3 bonds, so it can have one more hydrogen. This has 2, so it can have more 2 bonds to be 4, so 2 hydrogens. So this one 2 hydrogen, this one 2 hydrogen. This one has an OH attached to it through an extended line, and there is 1, 2, 3. So this one 2, 3. There is a total. There is 4 bonds, and it can have no other bonds. This carbon, so it has 0 hydrogen. Moving on to this one, so it has 1, 2, 3. 3 other bonds, and it can have one more hydrogen. And lastly, this has only a one bond, and there is 3 more bonds it can have. So it can have 3 hydrogens. This can also have 3 more bonds, so it can have 3 hydrogens. So if you count all the hydrogens that we just counted, so we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I counted wrong. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it's actually 17. So step 2 was counting the number of hydrogens, and we see at the last step, step 3 is to see whether there is any functional group or whether there is any other sort of uh, atom attached or other sort of group attached. So we see the functional group OH is attached here. So we have something else that is OH. So in total what we have is C10, H17 and an OH atom. So this could be Cl, something, anything extra that is attached like this. So we were asked to give the molecular formula, so we don't have to do anything with it. So that is like this. We have C10H18 or we could write this way, that C10H17OH. So this H you can omit and write as 18, or you could write this H as well. Now this next question is, what is the empirical formula of hexamine? So what I said, that every node or every free kink, so every free end and a free kink, so kink is this, meaning there is a bending in it, and end is this, like this end. So every free kink and free end represents a carbon unless something else is substituted. So let's say N is substituted here. So this represents, this corner is not a carbon anymore, this is rather a nitrogen, and this end containing OH. So now this end doesn't contain any carbon, this contains OH. So our first step was to count the number of carbon atoms. So let's start it from here. So this corner was is or this kink is actually substituted by another atom, so this is not counted. We have this kink, so we have one carbon, we have another carbon, three carbon, four carbon, five carbon, and six carbon. We see no other free kinks, so we have four carbons. So we have one, two, three, four, oh, five, six. We have six carbon actually. I'm sorry. We have six carbon, we have six free kinks. Moving on, the step two was to count the number of carbon atom, the hydrogen attached to the carbon atom. So for this step, we have to see the number of bonds that one carbon is making. So it is making two bonds. It can make two other bonds. So it can have two hydrogens. Similarly, we see one, two lines going away, meaning it is bonded to two other. So this carbon is bonded to two other two other something. So it could be bonded to. So in here it is bonded to nitrogen. This could be also be bonded to carbon or anything else. And this is also, this is not the matter what it is bonded to. The matter is that the concept or the fact is what we need to focus on is that there is single bonds, and we can have two more bonds in carbon. We know it can make four bonds, so it can have two more hydrogen, so 2H. Similarly, this corner has two bonds going away, so it can have two other bonds, so it make four bonds, so it is you can have 2H. So we see that all is having can have 2H. All kinks or all carbon can have 2H bonding, because we see no carbon having double bond, or we see no carbon or no atom being uh, attached to any other functional group. For instance, this, if it was like this, so it would be bonded to one, two, three carbons, and we would have written one H here. So we see no cases like this. And if for example, let's say if there was double bond, so one, two, three bonds, and we could have only one H here. So these are some special condition, but these are not here. So we don't have to worry about those. So if we in total, if you count the number of hydrogens, what we see is that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 such hydrogen carbons. And the third step is to see whether there is any other things, for instance, other groups or other atoms attached. So we see three nitrogen, oh sorry, 1, 2, 3, 4. We have four other atoms, which is the nitrogen attached to this molecule. So we have four nitrogen. So in total, we have six carbon and 12 hydrogens, and other, which is we have no four nitrogen. And we were asked to write the empirical formula, so we must simplify this. Simplifying this, we have If we divide it by 2, C3, we can have H6 and A9, and we can have N2. So now we have 3 and we have 2, so we cannot divide it further, I guess. We have to end it here. So this is the empirical formula. Moving on to the last diagram, we have so the diagram shows the structural formula of citric acid. Right, our first step was to count the number of carbon atoms. So this could be trickier because the other times, if there was any, uh, if there is any like any functional group attached, I showed it using a blue line. But this time there is no blue line, and this could be confusing. So now we have to look for free corners and free kinks and free ends. To our first step was to find out the number of carbon atoms. So the catch here uh, is that oh, so first let's do this. So this is a carbon atom, and we can do what we oh, first let's do this, that let's find out what are the extended lines, and uh, I mean let's find out the extended lines. So this corner, this free end doesn't actually represent any carbon. No, because it's an OH, and this is basically an extended line. This is called an extension. This is not an arrow, or this is not a skeleton of the carbon. So let's find the other such extended lines. So this is not any carbon, this is just an extension. Similarly, this end is not a carbon, rather it's an hydroxyl group, and this line is an extension. This line is an extension. This is an extended line representing nothing but and something else is attached to this carbon. So similarly, we have this. Uh, how do I? So we have this is an extension line. This is an extended line, and we also have these two extended lines representing double bonds, and two extended lines representing double bonds. So this end doesn't represent any carbon, rather these are extended lines. So we can call it EL if you want. So these are ELs, extended lines. These are not carbon showing arrows. So now let's look at the corners that we have. So first, uh, should we erase this, or let it stay this way? So our first step was to count, step one was to count the number of carbons. So we have one kink here, 1, 2, 3, we have 4, 5, and 6. We have 6 carbons. And now in this we are going to focus on those kinks and see how many hydrogen can it have. So this, the first one, it has 1, 2, 3, 4, 4 bonds already, so it can have 0 hydrogen. So this is not an OH, rather this is an annotation showing that showing number of hydrogens. So be careful on this, which I said previously. Moving on to the second kink, we have 1, 2 bonds already, so we can have 2 more bonds, so we can have 2 hydrogens. So let me not rewrite because I have written it already. Similarly, let's look at this carbon. So it has 1, 2, 3, 4. It has 4 such. Oh, this is an extended line too. I forgot. This is not a free end. This represents not a carbon. So this represents no carbon and nothing else. This is just an extended line. So you have to be careful about extended lines, and what is extended lines and what is just the skeleton of the carbon. So this has 0 hydrogen because it is connected to four other atoms or group. This has 1, 2, 3, 4. 2 double bond and 2 single bond. Oh, sorry, 1 double bond and 2 single bond, meaning it has already 1, 2, 3, 4, 4 bonds. It can have 0 hydrogen. This has two bonds, so it can have two more bonds, two hydrogen. This has 1, 2, 3, 4, 4 bonds, it is zero hydrogen. And we are over with this. So if you count the number of hydrogens, so counting the number of hydrogens, we have 0, 2, 4, 5, and we have 5, and here we have 6, 7, 8. So let's count it again. Let's just remove all this and count it again. So we have 1, 2, 3, 4. So for the time being, let's say we have 4 hydrogen. I don't know why did I write this. I think I counted this also, which could be done as well. And we have other 1, 2. So these are ketone groups, I guess. This is an aldehyde group. This is a carboxylic COO, but this group is actually an aldehyde. This one carboxylic acid. So for the with the double bonded O, we have 1, 2, 3. So we have 3 double bonded O's. Now our step 3 is to find the other atoms. So we have 3 double bonded O's and 1, 2, 3, 4 OH. 1, 2, 3, 4. Yeah, 4 OH. So in total, what we have is we have C6 and H. We had 4 here and we have 4 here. H8. So that is why I wrote 8 here. I think I counted all. And we have 3 oxygen and here 4 oxygen. 4, 5, 6, 7. So O7. So it's this C6H8O7. So this was doing some question, and let's do something very easy, I mean very fast. So if you are asked to draw the skeletal formula itself rather than from the name, so what do you do? So let's say 2-chloropropane. So step 1, so to know the carbon atoms and draw that many free kinks or ends. So we see our focus is on this. Our carbon atoms is propane and we have 3 carbon. So we can have just 3 ends or 3 kinks. So 1, 2, 3. So this represents carbon, this represents carbon, this represents carbon. It could be like this 1, 2, 3. So it's 1, 2, 3. So it could be in any way. Moving on. So it has 1, 2, 3 carbon. Step 2 is to add other atoms by extension, by extending from that carbon. So we have 2-chloro, meaning that on the second carbon we have a Cl attached. So this is the second carbon. We extend a line from this carbon and then we write a Cl, which I already have done it. So what I said that this arrow doesn't represent any carbon, but this is actually an extension representing the bond with chlorine itself. So this is the second step. So I've written it in pencil over here, so I don't have to do it again. So let's say if we are like we are suppose so this is the second question is this 1,2-dichloropropane. So you have to look at this first. It's propane. So it is 3 carbon with single bond. So we have 1, 2, 3 kinks, and we have dichloros. We have to have 2 chlorine, one at the first carbon and other at the second. So we could this could be this also, that uh, this could be the first carbon, this could be the second carbon. So it's vice versa. You could do any of them. These are isomers. Maybe positional isomer. No, no, not positional isomers, because you are counting that as first carbon. So based on your counting, you could have done the other thing. So moving on, we have dichloropropane. So we need to have 2-chloro on the same thing. So propane, so we have 3 kinks already. Ane, meaning you have a single bonds, no double bonds. So that's done. And now we have to have dichloro. Dichloro meaning two chlorines. So at first one at the one and the last one at the third. So it's, if you consider this as C1 and this as C3. So we have chlorine at the first carbon and chlorine at the third carbon. Similarly, the third question is dichloros. We have already drawn a propane, and now we need to have dichloro, means two chlorine, both at the second carbon. So this is the second carbon, and we have extended lines from both, and we write Cl and Cl here. Sorry for overwriting, but you can already see it written here. So I think this is a good overview for getting a grasp of the skeleton formula, of the skeleton structure. So we will keep you up to here, and we shall see you next class. Goodbye.